It'll be slightly repetitive. I just want to record. So my apologies. I forgot to hit record. So for those who are not here, we started talking about parallel load registers. So parallel load registers are, we just have, so consider a D flip-flop. I've got 4 of them here. And we just have hooked all the clocks together so they work in unison. They're in parallel, hence the name parallel, right? Data doesn't flow, that flows from one side to the other, but they're basically independent of each other. But we're going to group them together now. And we group them together for the purpose of building a computer. We've also hooked the resets because, as you notice, when we make D flip-flops, resets are a pretty standard way to make sure we can clear things out. If there's ever a problem, it allows us to fix things. We do it at boot time initially to clean stuff up. Then if we just put the data right into D, that's just a kind of typical register, but every clock pulse we will load. And we don't necessarily want to load every clock pulse. Now, there's a couple ways we can handle this. We could, use the clock and only send clock pulses when we want to do a read. Or we can build what's called a load register. And to make a load register, we just put a combinational circuit out front. We have the data come into it, and we also have the Q, our current state, come into it. Then we have a signal called load, which picks between the two of them. Right? And so essentially, this is a design to do this. Now, typical way you do it is I just copied them here and then did the details. Right? I've got my Q and my D come in, and then I pick which one do I want. Either the negated version of load or the double negated version of load, which goes back to load again. And as I mentioned before I hit the record button, the double thing just creates kind of a buffering onto it, which is useful for timing issues. Now, if you remember back, this is an identical circuit to what you had for a MUX. So, we kind of usually do this as kind of like a fancy thing and say, ooh, look, this is a load register. But I will note that this is identical to taking a MUX, and we use the load as the address selector. And if load is high, we want to load data in. And if load is not high, we just want to have our current state go in. So that's actually what you're building here. And I've mentioned before, MUXes are kind of like our friend in a lot of places. So that's really what to build. So if you look, the book will give you something that'll look pretty close to this. But when you look at it, I want you to think, oh, they're just building a MUX on the input to determine which one they want. And they either feed the current state back into it, which is doing a hold or a memory storage, or they let new data go in. All right. Do we feel good? Thank you, Jake. All right. So this is one type of register that's out there. This is what you typically deal with inside of when you have a laptop or a computer, or even a small thing like a Raspberry Pi typically is like this. Often when you get to really small embedded systems, and not just there are some larger ones that are just older chips from a few years ago. But when you get to really, really small ones where everything is super important space-wise, we'll do what's called a serial register. They're useful for a few other places. But a serial register we handle in a slightly different way. We literally feed them in one to the next. So this would be a 4-bit serial register. So on the other one, I had mentioned, that I had D3, D2, D1, D0. These ones, again, you could do in a lot of different orders, but let's just say this is our register bit 0, register bit 1, register 2, register 3. So this block, and again, its clock would be hooked up together. Its resets would be hooked up together. I'm not going to draw them again. I think that's pretty obvious. Um, yeah. But the trick on this one is to get this pulse in. How do I load something into this, and why would I build it? So first, let me talk about how I would get something into this. And so if I wanted to load the number, say like 1101, say I want to load that into here. I should put my clock. So if I give a clock pulse and I put the initial, the least significant bit, I put it on. I get a single clock pulse. That one will come in to here. It'll be stored in this first spot. I can then, since I only gave a single clock pulse, I can change this and it doesn't change anything because no new pulses are coming in at the moment. I give it a single pulse and then it's flatlined. Right? The one is in here. Then I take the second bit, I put it on the data, and I give it another pulse. When I do that, this one is currently on the D line. When that pulse comes in, the 1 moves down and the 0 moves in. Does that make sense? Thank you, Alexander. Okay. And then I just keep proceeding to go through each one of these. Right? I put the 1 up. I give it a pulse. They all shift down. The 1 moves over. The 0 moves over. And the 1 moves in. Load up the next one. Give it a pulse. They all shift down again. And it's in. Now, if you notice, to put in a 4-bit number, it takes 4 times as long as it normally would if I was doing a parallel load. Because if it was a parallel load, I would have just gone 1, 1, 0, 1 into my parallel 4-bit one. And I have my clock, which for that one is always running. And then I have a load signal, and I would just set the load signal high, 1 clock, the whole thing comes in. And I'm good to go. I'm done in 1 clock cycle. This took 4 clock cycles. Now I could do this instead of kind of delaying. I could just literally do 4 clock cycles. I know what I need. I would load 1 at a time into it. And so I could just do that very, very quickly. But it's still quickly on the load is still relative. This is 4 times longer than this. So you can imagine as the size of my data gets larger, this becomes more and more expensive. So if I was dealing with a 32-bit system, this takes 32 times as long as this one does. Now, often you're not going to deal with a serial register that's 32 bits. Very often 4 or 8 bits, because these are very small machines. Sometimes, only 10 or 12 even. Right? They're usually the much smaller systems. But there is actually a good reason for this, because you might go, why? That's so slow. It's so inefficient. It'd be so much easier to do this. Well, the reason why is actually on here. If you count the number of wires going in and out of each one of these units, right? This one takes, right? There's 4 lines going out. There's 4 lines going in. I need a load, a clock, and technically speaking, there's a reset here. So I've got on this 11 wires, dead minimum. That's not even counting power and ground. So technically speaking, I'm up to 13. Whereas on this one, I've got 1 data in, I've got 1 data out, I've got a clock. I'm not even going to do a load. It's just if the clock goes, it goes. So you're going to have to control the clock before. I'm not going to give you the parallel feature. Um, there would technically be a reset on this. So you can imagine I just have a reset down here. So I've only got 4 on this one. So you got 4. Well, I guess now I got power and ground. So I got 6 compared to 13. It's a significant savings space wise. Um, this, and when you go to small surface mount technologies, that's a huge, huge savings. When you go to 8, that's just pure advantage. Those extra 4 bits add 8 more bits here. It doesn't add anything here. So that's kind of the neat thing. It makes it slower, but this is 6 bits and it doesn't matter how much is in here. This one just keeps getting more expensive. So at minimums, it's 13, but it could be 21 if I had 8-bit numbers. And if I go to the 12-bit, that would take it up to 29 bits. This still keeps staying 6 because I still only have 1 bit coming in and 1 bit going out. What's really expensive on chips, believe it or not, is wires, number one, and power and heat, basically. So here's why this is so important. The contents of what you can put on a piece of silicon, right? The silicon, and we build it up in layers, is basically a volume. The contents, what's inside this box, I attempt to draw a 3D box there. Make it look more hidden, right? So what you build, gate-wise, memorize, things like that, is a volume, which if we have one length on the side, it's the length cube. So the amount you can build inside the system is growing as a length cube. If you look at the ability for either heat to come out or wires to come in, they've got to cross the surface. So they are proportional to the surface area. So, things that come in and out, right, which is your data transfer. So we use X for transfer. So data transfer, heat, so on and so forth. Any of those have to come through the surface area, and so they are proportional to L squared. So as we get more and more stuff concentrated inside bigger and bigger chips, your limiting factor is always going to be your data transfer. You just can't get enough wires in, right, to be able to do things. That's your penalty. You can't get enough heat out. To get for really small and higher performance things, people even use the wires themselves to transfer heat out. Right? That's how critical a lot of this type of stuff is, because surface area is much more expensive. So as we get smaller and smaller processes, and you'll hear about different sizes that people get down to on ridiculously tiny designs that we're fabricating things on. They usually mention their line width, and you're down to nanometers. It's ridiculous on the scale that we're at. So when we're dealing with like a 10 nanometer design, we're saying the line width is 10 nanometers. That's how wide a wire is. That means there's a lot of stuff I can pack inside this volume, but that means commensurately it's very difficult to get the wires across the line. So building things in here easy, getting data and other things in and out hard. So therefore, if I can get something like a serial register that allows me to get a very efficient small number of wires while handling a lot of stuff in, it's often the only choice we have to deal with. So when I'm trying to get something that's really small, an embedded system that's really tiny to do some type of a control in a microwave or something else, it doesn't need a giant amount of stuff. You don't need the highest performance in the world. so you can tolerate the slower loads and things of this sort. Plenty good enough with these type of shift registers. So does the motivation for why I want a shift register make sense to people? Awesome. Okay. So now we've got this shift register. Let's say I want to, with a shift register, parallel registers, you can just do everything you normally would do with. So I'll kind of keep going back and forth between these two. So you can imagine if I have a parallel register, and often to save space, I could just say, right, the slash on it tells you the number of wires. So I can have some data line that's coming in here. We have another data line, another 4-bit coming in. Maybe this group I'm going to call register X, and this I'm going to call register Y. If I wanted to transfer register X to register Y, all I'd have to do would be to hook it back around. Right? One clock cycle, boom, I could copy. Now, if I wanted X to hold its value, I'd have to transfer it to both locations. But that's still very doable. We'll talk about how we can make registers to do this. This is part of a universal register that allows us to move things around. The key idea is we put a bigger multiplexer. It gives us the options to transfer new data in or hold data, things of that sort. But for the moment, we can just see it's easy to move data around between these registers. So that's register transfer. You'll notice you've heard that term before, register transfer, with register transfer level, RTL. When we go to do designs, since pretty much everything in a computer looks like this, right? Y equals X, which is what I just had before, right? It means take the value of X, keep it in X, but also give it to Y. Right? At the end of that command, X should have X's value and Y should have it. So all I have to do is transfer. So the muck settings and everything else to feed X back into itself and then feed X over to Y simultaneously actually does that command, Y equals X. It turns out almost everything you can describe as a basic programming statement can be thought of as transferring data through some type of combinational circuit to another register. So if thinking at that kind of high level is what's called register transfer level, it turns out that's a very easy way to do a design. So let's say I wanted to do X is equal to X plus Y. I want to do a summation circuit. Again, I can take my X and Y, I can feed them into an adder. And you've all built adders inside your lab. And then we just take the output of the adder and we would just feed it around to the input. So that's a really simple circuit. You've been building these already. These each have 4-bit wires coming in and 4 coming out. And so you just build, you could do this by the ripple carry, you could do it by a couple different techniques, but ripple carry is the one that you've built so far. So literally the adder subtractor you built, you could put right in here, and this is just what's going on. Sources XY goes through an adder, and the destination is X. So I'm transferring from these registers to this register through this summation circuit. That's register transfer level. Extremely easy inside a parallel register. How about a serial register? Well, let's go through those two operations. First, copying one thing to another while preserving, right? And the second one to do addition. Right. First operation. I've got a serial load register now. Right? I've got a serial register. I've got a D input, a Q output. I've got a clock. I'm going to call this one X. I've got a second serial register, D input, Q output, and a clock. And I'm going to call this one Y. So if I want to do Y is equal to X, well, all I have to do is take Q to D. The output of this one has to go through, and I need to preserve it. The Q comes back around. And you might say, well, that's exactly the same as what we had before. Yes, with one extra thing we're going to need to do. In order to transfer this is 4 bits, but I've only got one wire. What's going to happen is, imagine this has the number 1101 we had loaded before. And this one, who cares what it has? I'm just going to put 4 X's. Right now, this Q shows 1. So when I give this a single pulse, this is going to, this 1 is out on the line here, which means it's coming back around into X and it's going into Y. So Y shifts down, and the 1 comes in. That 1 simultaneously shifts around. These shift over, and that 1 shifts in. And now there's a 0 on the line. That's the first pulse. And then I give it a second pulse. That 0 comes around, shifts in, 1, and the 0 shifts over here, and 1 more of these drops off. That's the second pulse. Now, this one is on the output line because they all shifted. And I give my third pulse. That 1 comes around. Manually do the shift now. So the 1 is going to come out. These ones move over. 1, 1, 0. The 1 that was on the line comes in. This all shifts over. I get 0. And that 1 shifts in. That's the third pulse. So far, so good? No answers. Uh-oh. Okay, are we lost or are we just 109? I got a yes. Thank you, Ashley. So I do want to make sure that it's really easy, right? It's right after lunch and, I'm the only one talking. So I do want to just make sure that it fits. I see an S0 and M. Mistyped. Okay. So was S a no? No worries. Okay. Totally awesome. I just don't want to get you guys lost. So the ideas are not too hard as long as we keep them in check. But there's one thing we're going to want to add to the circuit to do this perfect, right? This is my last one. I've done 3. I have to do a 4th one, right? So this 1 is out on the line now. I give 1 more pulse, right? So that 1 is going to go out and get lost. The 101 moves over. This 101 moves over. The X drops out, and that 1 gets shifted in. So now I've got 2 copies. I've got to get exactly 4 of these, and I don't want any more clock pulses. Otherwise, it'll keep doing stuff and get my numbers messed up. So what I do is my clock is not going to be a normal clock. I'll put both of these together. We're going to get an AND gate. And your normal clock is going to be here. And what I want is I want nothing, nothing, nothing. And then for 4 pulses, I want exactly that, and then nothing continuing on. And I've got to get this from just like a constantly running set of pulses. So I'm going to take this and I'm going to AND it together with kind of a load signal. So my load signal will last exactly 4 clock periods, and it will just be a 1. And at all other times, it'll be a 0. And that's going to be this second input here. The load and clock. So if this is load, this one is clock, and that gives me this all important, exactly 4 edges right when I want it signal. You can do that easily with this load signal. When you get to the point when you want to load something in, all you have to do is fill a 4-bit register with all ones. So you just do a set, and then you have the input be zeros. And as basically that one feeds into here, it'll give you 4 ones, and everything else is filling in zeros. So after that, it'll be all zeros. So when this command comes up, that's one of the few cases you actually want a set button. Or you can do a reset and then invert the output. Either way makes you happy. If that's the case, then you have to load ones into the system afterwards. But that will give you a load signal. So the important thing to note is we're going to do this AND on the clock. If you remember last time, we had options, essentially a MUX on the data at the start of class. For the parallel, what we're going to do for our serial is going to actually be this, because to hold it, I can't just hold any one bit. I might be partway through copying something. So we want to actually do it such that you have to control it to get exactly 4 of these. So anyway, so that load signal is what's going to be our extra addition. But with that load signal on the clock to do yes, so I get exactly 4 of these, now I've got a functional system, and then I can just feed them back. It's only 1 wire. Right? 1 wire between them, 1 wire fed back. Takes 4 times as long again. But space-wise, it's efficient as all get up. Okay. So that's the ideas for y equals x, a data transfer. Nice and simple and straightforward. We're good? Awesome. Okay. I'm presuming you all feel comfortable with this drawing. Let's add another complexity. Now we want to get x equals x plus y. So we want to do an addition. I could put it to a z, but a lot of times we do this type of x equals x plus y. It's a very common one because in loops we'll often do a summation. Sum equals sum plus the next number in your sequence. Those type of what's really called so there's potentially 3 addresses. We call these 3 address equations. But a lot of times the one on the left side is the same as this. This is why you'll also see the x plus equals y, which is done in C this way. So if you've ever seen that, it's for this, and it's because there's just a lot of those, like that sum equals sum plus, next number type of thing. We call these 2 address ones. We have shortcuts for that command. That's just a side note, but it's an important one that comes up a lot. How do we build an adder? Right? Well, let's think about what we're getting from our serial numbers. So let's say I have my first serial one. Assume I've got a clock and I put that whole ANDing circuit on so I can shift it if I need it. Data in, Q out. Data in, Q out, and this is Y. Right now, I have the least significant bit of each one in here, right? The lowest number. So imagine the top one at this number. Let's just assume they're straight binary, not in 2's complement storage. So I'm dealing with 13 here. And let's say I want to do 13 and 6. I don't know. Fair enough. Now, we know this is going to take more space to hold, but the idea will still work. I can do this one at a time. I can do 1 plus 0 gives me a 1. Carry nothing. And then I can proceed to the second one. 0 plus 0 plus 1 is 1. Carry nothing. 0 plus 1 plus 1 is 0. Carry a 1. So it'll work, right? I can look at this. There technically was an initial 0 here. That means I've got my two numbers. I can do them one at a time where I'm just dealing with one of these. And I calculate the carry and the sum, but I have to hold my carry to the next time period. What that means is I can have a single bit adder. A single bit adder is what we call a full adder, right? So our full adder has three inputs, X, Y, and a carry in. And it gives me a sum and a carry out. And I want my carry out to become carry in at the next time period, but I got to get a 1 cycle delay. What I do, I get a D flip-flop hooked backwards. Notice I have D on the right. I have no choice because I have to run the D into here. Otherwise, I give you this weird cross thing. So, and I initially set it to 0. So I give it a reset, boom, and it's a 0. So when I first am doing this, I would see 1, 1, 0, 1, 0, 1, 1, 0. I'd see a 1 here, I'd see a 0 here, and I'd see a 0 here. And it'd add it all up, and I'd get a sum of 1 and no carry. Then once that, I would time my thing so that this has time to finish to calculate. And then, boop, clock pulse. And this new 0 would come in. And I want this 1 to come around into X. Because that's my sum. And I want my summation to go back into X. Y should hold its own value. I'm going to take the same thing out from Y and feed it back around so that it holds its own value. Now I've got a basic circuit. Does the basic circuit make sense? We'll run through the whole equation. Yay. Okay, awesome. So we did our first calculation. We got a 1. That 1 comes in. So the 1, 0, 1 will move over. 1, 1, 0. The 1 comes in. The 0 from Y comes around. It comes in. And this one has the 0. So now I have a 0 here, a 1 here, and a 0 there. Next calculation, it's going through F. The second it gets new values on its inputs, it immediately starts calculating. And it calculates a 1 and a 0 again, which is good because that's what I should get for the second time. All right. Next clock pulse comes in. This 1 is being fed in here, so this shifts over. 1 comes in, and the 1 from this feeds back around. And the 0 comes back in. And now the inputs are 1, 1, 0, 1, 1, 0. So that calculates the number 2, 0, 1. Next clock pulse comes in. These all shift, and the 0 comes in. And this 1 comes back around, and everything shifts down. And a 1 comes in. Now I have a 1 here, a 0 here, and a 1 on this bottom line. So now I just did that line. Now I'm doing this line. The very last, this is my fourth one. So that's still going to calculate the same exact number. Right? The 0 will come around, a clock pulse comes in, this shifts over. This 0 comes in, and everybody shifts down, and that 1 comes in. And then no more clock pulses. Now, what's in here? So let me do the last bit of our number, right? So 1 plus 1 plus 0 gives me a 0. And I should have a 1 in my carry bit. So this goes into X, 0, 0, 1, 1, 0, 0, 1, 1. There's a 1 in my carry bit, which if I want to, I can pass that out. Because inside your hardware, when you get to comp org, you can actually take this carry bit and it gives you important information because this is 13 plus 6, which is 19. And 19 is 3 plus 16. So that carry bit actually is a value. It just, there's not enough room to hold it. But a computer can look and say, hey, look, I shouldn't have gotten smaller, but I did, right? We can set a flag saying, oh, there shouldn't be a 1 here in regular binary addition. The test is a little different for two's complement, but for binary, if there's a 1 there, something got carried out. So I can look here and go, oh, there's a 1, and the computer can actually process that and determine, does it want to expand the memory size? And now you may say, hey, I can't just add new registers. That's true, but I can use 2 registers to hold 1 value. So I can determine, hey, maybe 4 bits isn't enough. Maybe I need 8 bits. So I'll use 2 memory cells to hold it. I deleted okay. But anyway, that gives me a test. So I can still access that. I haven't lost anything. And if you notice, it did the calculation perfectly. So all the pieces of information are still there. It just took me 4 cycles to calculate it because I had 4 bits. But look how tiny it is. And for my unit, I only need a single full adder. The really sad thing is that it takes you that long for a ripple carry adder with parallel registers too. So this is not actually any slower calculation wise, but it uses a lot less hardware, which means it's more compact, it's less power, all kinds of stuff we like on embedded systems. So you can see on this one, and I can do the same adder subtractor trick that I did on the other point in XOR here with the mode bits and, you know, do I put a 1 into the carry? So you can do the same adder subtractor trick as you wanted before, but the big thing is it's a lot smaller. Now, on parallel ones, ripple carry is not the fastest. We talked about carry look ahead and some other things. I can't do that here. This one is always going to be slow. But for the slowest system, you know, the simplest one that's done, we're every bit as fast as that is, and we take a lot less space, which, you know, space is a big thing to us. All right. We feel good about addition with serial. Awesome. Okay. So now we've gone through, we've done parallel, we've done serial. So what would happen if I wanted to go from parallel to serial, for instance? And you might say, why on earth would I ever want to do that? One other area that we often deal with a serial register like this is for doing data transfers on some type of a bus. So often we have a single wire available for us, a data wire. So if you imagine I have a data wire on a bus, I actually want a serial register to drive it. And this is partially why buses are slow, is because I send one bit at a time. And I could either put the most significant bit first or last. That's not necessary, other than whatever the bus protocol says. But obviously I can pick up a serial register. And on the other end, my receiver also has to have a serial register. Okay. So another spot that we deal with serial registers is when we go to these type of bus transfers. And if you think about it, USB is this way. A huge number of our ones. Ethernet sends one bit at a time too. Right? So a lot of these, again, to keep the wires small and everything else, send one bit at a time, which means you need serial registers to be able to accomplish this. So that's a common situation. So that means on this computer, computer one, here's computer two, I have to take my internal parallel registers Okay. I'm pressing too hard. Okay, let's try this one. Okay. So I've got to transfer from my parallel to my serial. But how exactly do I do that? Okay. Parallel internal register to a serial register, that's kind of a question. The second one is over here, I also have a parallel register. And I've got to take the serial and pass it here. So both of those are kind of questions. So that's what we're going to answer. And one of the typical ways to do this is with universal registers. So very often we'll make actually a universal register here, and we'll give it certain features that we want. So this is kind of motivation. Parallel to serial, serial to parallel are both things that we want. I'm going to show how we can do this now. For the first case where I want to go parallel to serial, imagine I had my original 4 registers. I need to be able to load in series. So I've got some data coming in. Whatever my bit sequence is. I think I was doing 3, 2, 1, 0. For this one being bit 3, 2, 1, and 0. Pick your appropriate correct sequencing. All right. Now, assuming that is my sequence, I could want to load these data. I might also want to hold my current value. I might also want to shift them, right? And if it goes 3, 2, 1, right? That would mean I would be taking this value. If I shifted right, so think of them ordered this way from my left, right. Imagine 3, 2, 1, 0. Shifting right is going from 3 to 2, 2 to 1, 1 to 0. And the 0 dumps theirs. So from 3, just grab, I've already passed one around. From 3 into 2. From 2 into 1. From 1 into 0. So now the incoming one on here, right, if I'm shifting right, is some data input, which I could make on data 3, or I could do like a serial data in. Right? So the top one was hold. This one was load parallel. And this is shift right. Okay. I can have a reset on the bottom that's asynchronous. I could also have another option here for that. But let's say I want to do the other option too. What if I want to shift things back the other way? Which means 2 has to go around to 3, 1 has to go around to 2, 0 has to go to 1, and 3 has to go into 0. That's kind of ugly looking, isn't it? But that does a shift the other way around. So if I want to do a shift left, it's actually easier to draw in this format because 2 goes to 3. Right? So this is 2 right here. I just feed it up in. 1 has to go to 2. 0 has to go to 1. And then I have whatever I want to shift in here. Oftentimes we do a circulant where 3 goes around. I'm going to do that one and just say it's a circulant right shift. You could also do a 0. So you have 2 options. We could do 0 being shifted in. That's a traditional shift left. It's sometimes also called shift left logical because it's treating all this as logic. If you put here the value from D3 carried down, with D3 here, or sorry, Q3, oops, the output, with Q3's value placed here, then it would be called a shift left circulant. Think of like circle, because the value of 3 is kind of looping around and coming into 0. So it kind of circles around and comes back in the other side. So if I was shifting the other way, 3 would normally fall off, but now it circulates around. I can do the same thing with a right shift. Instead of having a serial in for my right shift, I could have had D0 come around. The reason why I didn't is because this serial input is something I need. On this one, I really don't care which one I do. I just want you to know about them. I've already written 0, so I'm going to be lazy and just leave it at 0. But I have those 2 options. When you do your course, you get into assembly language and things like that, and you deal with shift left, you'll have different versions, logical, arithmetic, and circulant. So these are 2 of your options. It turns out when you're doing shift left logical is, so we often call this S shift left logical. This one is shift left circulant, SLC. But only in the shift left case, shift left logical is shift left arithmetic. There's no difference. So I really only have 2 options in this choice. Anyway, that's a note for future classes, but it's how it ties into our hardware. So this is an arithmetic requirement. And you pick this based on what your assembly language manual, the design spec says, what should it be, right? Somebody says, hey, look, we want these assembly commands. Our choice of what value goes here has to match their assembly command. That's actually why you learn assembly. So if you're ever wondering why you learn assembly, it's actually assembly language is necessary to know how the computer is going to function so you can build a computer that works that way. If you don't know how it works, you can't build it. So assembly is not because we ever think you're going to assembly program. You might, but it's really low likelihood. But your big chance is that you'll probably actually have to build a design on. So now I've got 4 options here, right? Hold, right? Load parallel, shift right, shift left. And I put them in the same order on each because when you have 4 options, Easiest way to do it is put a mux. And this, to pick between four things, I need 2 bits coming in. That's going to be whatever my command is. If my command is a 0, I do a hold. The meaning for the particular bit pattern. If I give it a 1, I do a load parallel. If I give it a 2, I want to shift right load. And if I give it a 3, I'll do a shift left logical. I can erase that here. I was just recording my meanings, and I can put in my mux. Because mux is our great friend. Right, and now I have a great register that takes parallel data in, and all I have to do here, if I take this bit as my shift out, my least significant bit, to do a shift out, all I have to do is this shift right load. Right? And that will shift out my data 1 bit at a time. Right? Because this one will go out and then everything shifts down. And then what was in 1 is now in 0. So it'll shift out. And then I give it another pulse and then down it goes. And then 2, the data from 2 is in here and it goes out. I give it a clock pulse. The data from 3 has now made it down. That's the fun thing with the shift right. Right? Since I put that shift right in, if I give the command 2 and 4 clock pulses, this looks like a serial register, but I loaded it like a parallel register. So it's very easy to do. By having this serial in on that shift right command, on the other side, I can just hook this from my bus coming into here, and then a series of 4 clock pulses based on the same clock that's on the bus, right? It'll load the least significant bit, clock pulse comes, right? Least significant bit shifts down, right? Because I'm doing a shift right. That's this one we barely use, but I wanted 4 anyway because muxes come in those packs. So I do my shift right, it shifts down. And I just keep doing that. Each bit in sequence shifts down. So again, that command 2 will do the output. It'll also do a load and input, the way we set it up. And then when I want to do parallel out, I just read all the bits. I can have a parallel out. If I use the least significant, I have the serial out data format. When I feed serial into the most significant bit, do a shift right, I ignore the other ones, I get a serial load under this type. But these are universal ones because I can hook them in parallel, or by using these mux commands, I can force them to become a serial. So I can switch the bit usage format. Right? So that turns this into a very useful, it solves both sides of my problem. Oh. No, well, cereal in that format, Justin, would be tasty, but I do mean cereal as in sequence. Yeah, I'm kind of hungry too. I haven't had lunch yet, so it's like almost 2. We have 5 minutes left. Yeah, we have been talking about cereal too much. But now we've got universal cereal, which I don't know what that is. I guess cereal both old people and young people can eat. Like bran flakes with sugar on it. Actually, that sounds gross. But this, yeah, I don't know, maybe a healthy version of Captain Crunch or something. In any case, we've got kind of a setup that works. So now we've got a registers, we've got 2 types, and we've got kind of this hybrid one doing muxes. that lets us kind of function between them. But that actually gives us the functionality to now do bus data transfers and all kinds of other fun stuff like that. So if you've ever wondered how we do those bus transfers, there you go. And in later classes, we can actually build these and implement them when driving different types of bus protocols. So, all right. Do we feel good about the registers? Okay. Um, so we've got formats. I just want to open it up for any questions any of you might have on, any aspect of the course. You can either unmute and speak, or you can type it in the chat, whatever you feel comfortable with. Class Thursday. Yes, I don't know what happened. I had made WebExes for all of these, and then I came back and looked, and they're all gone. So there will be class on Thursday. I'll try to remake the thing. I was looking at last night, and I'm like, where did it? Even today was gone. So um, evidently, Canvas and I are having our continuing love-hate fest. I'm told to love it, but I really hate it, and it hates me right back. But yes, class on Thursday. There won't be any more. I only had to miss classes because my WebEx was being used for the recruitment in the department. There has to be one thing that the candidate logs into and we interview them on, and I'm the hiring chair, so my account got used. And unfortunately, we've had candidates on Thursday. I've been fortunate. There were 4 candidates that actually only interfered twice. So I'm at least happy I only had a 50% hit. But yeah, no, Thursday class, from now on, there should be no reason to have to miss. So yes, once I'm off here, and now that I'm really hungry from talking about all this, I'll probably eat my lunch and then then make the WebEx. Any other questions? Is a counter pulse driven. So we're going to deal with a couple different types of counters. A lot of the counters we're going to deal with will be like, for instance, like a Johnson counter and things like that are going to actually be serial style. And that there's some really neat things you can do for very efficient counters under that type of a pattern. There'll be other ones where we're going to have to build something that does a regular incrementing, or we'll talk a couple different ways to build them. But there has to be something. So often we'll have a clock, and then we'll have like an input that says count now. Some of them just will run continuously. You've seen some of these examples inside of your labs where it's automatically, it's always counting. And at some point we'll have a reset based on however big that's counting. So we do those type of automatically always running and counting ones for things where we need to slow down a clock. Like for instance, on your FPGA boards, fucking talk. FPGA boards have a 50 megahertz clock. That's way too fast for a lot of things we're dealing with. Like a human eye can't process that. So we've got to slow it down like about a factor of 1,000,000, right? So that it gets down, and that would get us to 50 hertz. So ballpark about 1,000,000. Uh, so that will often go. There are some where that, I'm presuming you mean a pulse driven, like an input comes and says, go count. Don't count. Right? And it just does one at a time. So the continuous ones like are used to slow down a clock to a slower amount, to generate them. Those ones often are not. You'll see it like computers are usually running at, say, for instance, like 2 or 3 gigahertz, which is, 500 picoseconds, down to maybe 333 picoseconds. That's very fast. If you look at the timing on a computer, you can only get outputs in microseconds when it's counting things. So that means when they're doing the counting, when they do their timing, there's actually a system that's slowing it down, and it's got has to count anywhere from 2,000 to 3,000 to slow the system down from um, 500 or 333 picoseconds to get to a microsecond. So that's another example where it's just a continuous run counter, and then it just overflows and continues again. The pulse driven, where you just say, add another number, kind of like what somebody does counting people coming into an arena, click, click, click. The automated computers counting cars going into a garage, things of that sort, will have a particular pulse that's coming in, that's an input. And we'll handle that rather than just let it run. There we go. So we do those type of ones by setting up one of our areas where we'll have like 0 as a state and 1, 2, all the way up to whatever n-1 that we're trying to count towards. And then on these lines, we'll have a 1, which means count, and then we'll have a 0 for don't count. So when you see things like this as your state, that's classically a counter. If I just hold 1 down, it works like the first type, continuously counting. If I send it just a single 1, boop, right? And then it's 0 afterwards, then it works as the kind of pulse counting. And we've already started to see this. This is why you have to do the previous section before this section. So if you're wondering why did we wait, well, because counters look like circles or rings. Does that clear that one up? Awesome. And we will get into this in more detail because counters are coming up. It's a big issue for us because it's really, and pretty much every design has a ton of counters in them. Any other questions? All right, well, I don't see any more. I know people have other classes, so I'll cut off. Sure miss seeing all of you. Wish we weren't having to do this remotely. But I do hope everything's well and you're all healthy. So good luck. God bless with your classes. If you have questions for me, send them over. I'm happy to answer them as best I can on email. So hope you're all well. Thank you. I will. All of you have a good lunch if you haven't had it already too. And a great day as well. All right. Miss you all. Have a great day. See you on Thursday.